Hello, I'm John Doherty and welcome to this video, part of the nuts and bolts of using PEST, and PEST++ series. This video is on implementing ensemble space inversion. Now, ENSI, as it's sometimes called, or ENSI for short, is the subject of other videos, but in this video we'll concentrate on implementation details of ENSI. But before we do that, let's just give a little bit of context before we describe the nuts and bolts of implementing ENSI. To do that, I'm going to say a few words about history matching in general. So when we history match a model, there's normally a couple of options available to us. We could calibrate the model, for example using PEST or PEST-HP. When we calibrate a model, and this is the subject of other videos, we seek a minimum error variance solution to an inverse problem. We seek uniqueness, but we seek uniqueness in a special way. We may have lots of parameters, we should have lots of parameters, but we define a fallback position for all those parameters, and we seek minimum departure from that fallback position. There's many ways of looking at this. Another way of looking at it is to say we're seeking the simplest way to fit the data, or we only want heterogeneity to arise in ways that are supported by the data, nothing made up. Now, if we do everything correctly, it can be shown that if we then use that calibrated model to make predictions of system behavior, those predictions will have minimum error variance. That is, they will lie near the centers of their posterior probability distributions. So uniqueness gives us something nice, the ability to make predictions that are at the centers of their posterior probability distributions. And we attain that by seeking uniqueness, seeking the simplest, normally, parameter field that is compatible with the data. Or we can do Bayesian history matching using, for example, PEST-PPIES, an ensemble smoother. In this case, we seek the opposite of uniqueness. We seek many ways to fit the calibration data set. And then by running the model with those many parameter fields that all fit the history matching data set, we're able to sample the posterior probability distribution of any prediction that the model makes. Now, the nice thing about that, of course, is that we're satisfying the imperatives of decision support modeling. Decision support modeling requires that we quantify the uncertainties of decision critical model predictions. Another nice thing about using IES is that it's numerically cheap, something we'll talk a lot more about. So using IES for history matching ticks a lot of boxes. It's numerically cheap because the number of model runs per iteration of the inversion process is equal to the number of realizations that we use and not the number of parameters that are embodied in those realizations. So you could ask, why calibrate at all? Why not just use ensemble methods and go straight into numerically cheap parameter and predictive uncertainty analysis? Well, there are some nice things about calibration. And this is where we're implementing what I call modeling as inquiry. We seek the simplest way to fit the data. But if we're a little bit surprised at the parameter field that emerges from that history matching process when we're purposefully seeking minimum departure from something we expect, then we've learned something. We may have learnt that our prior parameter probability distribution isn't as we thought. Or we may have learnt that the model has structural defects, so parameters are compensating for those defects in order to fit the data. Either way, we've learned something important, something that would be much more difficult to learn if we were seeking many solutions rather than one minimalistic solution to the inverse problem of history matching. Another nice thing about calibration is that as a byproduct of the process, we obtain a sensitivity matrix, a Jacobian matrix, and this can be used as a basis for linear analysis. Linear analysis is easily implemented using tools available through the PEST and PyEmu suites. We can do things like parameter and predictive uncertainty analysis, parameter identifiability analysis, data worth analysis, and other things once we have that sensitivity matrix. So calibration gives us good things. So why do we ever not calibrate? Well, there will be occasions where it's just not feasible. If we have lots of parameters, which we often do, and a model that takes a long time to run, then filling of that Jacobian matrix, that sensitivity matrix, may become numerically impossible. It may just require too many runs of a model that takes too long to run. In that case, we really have, especially if the model has questionable numerical stability and finite difference derivatives lose their integrity, in that case we really have no option but to use ensemble methods, which is a pity. So why is PEST, PPIES and ensemble methods in general, why are they so efficient? Well, there's a number of ways to describe this, but basically they work in a subspace of parameter space. So unless we use localization, which we won't discuss in this video, when we use ensemble methods, we stay within a subspace of parameter space that is defined by the parameter realizations that we start with. And normally those realizations sample the prior parameter probability distribution. So here, for example, we have 3 samples of the prior parameter probability distribution. They don't fit the data well because they're samples of the prior parameter probability distribution. Then, through the magic of IES, these become morphed into samples of the posterior parameter probability distribution. They're samples of the posterior because they allow model outputs to fit field data. But because we're working in a limited dimensional subspace, we gain the benefits that we only need number of model runs per iteration is the same number as dimensions of that subspace, number of realizations in the ensemble. But as a consequence of that, we can't move out of that subspace. Any one of these samples of the posterior that we end up with is a linear combination of samples of the prior. So we don't get to move out of that parameter subspace. We gain efficiency, we lose a little bit of flexibility. And that can cost us sometimes. So what are the problems associated with living in a subspace of parameter space? We gain efficiency, but we may lose something. For example, if we've got a lot of data, there is definitely a lower limit on that subspace. The number of dimensions of parameter space that we work in has to be big enough to allow us to fit the calibration data set well. So there's a bottom limit to how much we can reduce the dimensionality of the subspace that we work in. Also, if a model is highly nonlinear, maybe we don't get as good a fit with the history matching data set as we'd like. There are difficulties in working in a rigid subspace of parameter space. So we may not fit the data as well as we'd like. The numerical performance of the inversion process may not be as good as we'd like. And there is a possibility that by sticking to a restrictive subspace of parameter space that we may incur some parameter and predictive bias. But that's just life. Every numerical advantage brings with it some disadvantages. We just have to be aware of what we gain and what we lose. So that provides a little bit of a context for history matching and dimensional reduction. Now let's look at ensemble space inversion, or ENSI for short. Now at the time of recording this video, ENSI is only a few months old, but it's already had some remarkable successes in calibrating big, slow, structurally complex parametrically complex models where nothing else seemed to work, so it has proven its worth already on the inversion battleground. So let's look at some features of ENSI that make it unique. Firstly, by using ENSI, by using ensemble space inversion, we are calibrating the model. We are seeking uniqueness. We are undertaking regularized inversion. We're seeking a minimum error variance parameter field that allows our models to make predictions that lie somewhere near the centers of their posterior probability distributions. But at the same time, we're borrowing some features from ensemble methods. We're working in a reduced dimensional subspace of parameter space. Therefore, the number of runs per iteration is equal to, roughly, the number of realizations that we're using that define that subspace. But at the same time, we're going a little bit further. We're not only working with realizations of parameters, but we're also estimating individual parameters that we select, at the same time as we're working with realizations of parameters. So ENSI has some features of traditional calibration where we estimate individual parameters, and some features of ensemble methods where we're working with realizations of parameters. ENSI is able to attain a high level of fit with a calibration data set normally, if the model is appropriate. Furthermore, it's able to do that even with calibrating complex models for which the relationship between model outputs and parameters is highly nonlinear. So ENSI is robust. To see a little bit more about how ENSI operates, let's just, for illustrative purposes, look at a pretend model here, a model of an alluvial valley, in which we've got observation wells, and let's pretend that these are the parameters that we're estimating. Suppose we're estimating a global value of kH throughout this entire model domain, a global value of specific yield throughout the entire model domain, global values of boundary conditions. So these are individual parameters that apply to the whole model domain. Now, ENSI is not restricted to working in parameter contexts like this, but it does work very well in these types of contexts. Suppose then that we have other parameters that provide the detail. Suppose we have kH and SY pilot point multipliers that multiply those global hydraulic property values within the model domain and along the boundary. So there'll be lots of these, many more perhaps than I'm illustrating in this simple figure. So spatially distributed parameters will be used to fill in the detail to allow heterogeneity arise where the calibration data set says heterogeneity must arise. Now, if we were to try to use IES for history matching of this simple model, it would work something like this. We generate a realization of parameters, and in that realization would be kH pilot point parameters, random values selected from the prior of SY pilot point parameters, random values of these individual global parameters. Realization number 1. Realization number 2 would be another random set, kH, SY, lots of parameters in each of these, and random realizations of our global parameters, etc. IES would then do its magic and estimate n sets of parameters, n realizations, where n is the number of realizations. It would try to sample the posterior probability distribution by effectively, this is not actually what it does, but it does something similar, estimating factors by which these are multiplied before being added together to give us new realizations which now sample the posterior parameter probability distribution. We're staying in that that subspace of parameter space that is defined by those samples of the prior probability distribution, and every sample is a realization which involves all types of parameters used by the model. Now this often works very well. Sometimes, however, things can go a little bit awry. Suppose, for example, that we have a calibration data set that tells us a lot about KH. Suppose that our prior probability distribution for KH is a little bit, well, it's not quite right for KH parameters. There might be patterns of heterogeneity, magnitude of heterogeneity, different from what we anticipated. That'll happen all the time, of course. IES can cope with that. It can bend these parameters, these realizations to fit the data, even though that data expresses heterogeneity that we didn't quite anticipate. That's not a problem. But in doing that, these other parameters might get dragged along to give us that good fit, especially if there's not much data which constrains these parameters. So this may introduce a little bit of bias to the parameters and the predictions that are sensitive to them. May or may not, but it's a possibility, something that can always happen when we're doing inversion in this way, working in this reduced dimensional subspace where each realization is comprised of all the parameters with which the model is endowed. ENSI works a little bit differently. With ENSI, we generate realizations of KH just as before. The final KH field, with which the calibrated model is endowed, however, is just a linear combination of the KH parameters if we design ENSI to operate this way. So in this case, these factors by which these realizations are multiplied are directly estimated by ENSI. So we combine the random realizations of the prior probability distribution of KH in a way that gives us a parameter field, a unique parameter field of minimized error variance to the extent it can be minimized in this limited dimensional subspace, a parameter field which allows us to fit the data. Similarly, we take our realizations of SY. ENSI evaluates, calculates, estimates factors by which they must be multiplied to give us our final SY field with which the calibrated model is endowed. And then these individual, global, non-realization parameters, they're estimated separately. So ENSI then is busy estimating factors by which parameter type specific realizations are multiplied, F1, F2, Fn, G1 to Gn, at the same time as it's estimating native model parameters. So some realization factors, some native model parameters. It's our choice of how this is done. So what does this give us? Well, in the end, often this gives us a really good fit with the data. It reduces the propensity for parameter and predictive bias. It generally, as I said, it allows us to fit the data often very well, even where the relationships between model outputs and parameters is severely nonlinear. Not only do we gain our history matching alacrity in nonlinear situations just because of the way that the inverse problem is formulated, but we gain even more robustness if we use PEST HP to calibrate this model and invoke its Broyden-Jacobian updating functionality. Now this is fully described in the PEST manual, but just a brief description of how it works. During every iteration of an inversion process, PEST HP calculates a Jacobian matrix. Then it updates the parameters using different values of Marquardt lambda and chooses the best update. But before it goes on to the next iteration, it improves the Jacobian. It learns something from the updates that it's just done and improves the Jacobian matrix and then does the updates again. And what it learns from doing that first set of updates can benefit it enormously when it does the second set of updates, particularly in nonlinear inversion environments. So put all this together and ENSI is pretty robust. The disadvantages are that, well, we're only calibrating, we're not doing uncertainty analysis. And if we're doing decision support modeling, we need to do uncertainty analysis. Having said that, we'll talk about this later, we can start our uncertainty analysis from the outcomes of ENSI inversion. If we've attained a minimum error variance parameter field and a good fit with the data, how we do uncertainty analysis after that can be done in a way that retains that high level of fit. So we continue to fit the data well if we do it right, while sampling the posterior probability distribution of our parameters following our original ENSI run. So that's the concepts behind ENSI. Now let's look at a few of the implementation details of ENSI as done through the PEST HP suite. These are the programs of the PEST HP suite that allow you to implement ENSI. For much of the remainder of this video, we'll see how they work together. But before running any of these programs, let's just have a look at what we have to do to prepare for their running, to prepare for ENSI-based model calibration. Now, preparing for ENSI inversion is almost the same as preparing for the use of PEST BP IES. We just need one extra file. So suppose that we were preparing for an IES run. Well, we'd need a pest control file and template and instruction files that are cited in the pest control file. We'd need a parameter uncertainty file providing prior probability distributions of model parameters. That's all we'd need. For ENSI, we need one extra file, and that's called an ENSI specification file. And as you'll see, this is very easy to prepare. So let's just look at a few details of these files. First, the pest control file. Just a standard pest control file. We tell PEST to run in estimation mode. Now for the case, that illustrative model that we've just been talking about, the parameter data section of the pest control file will cite global parameters. In the parameter data section, we'll have their initial values and their upper and lower bounds. In the parameter group section will be control variables that tell PEST how to calculate finite difference derivatives for these parameters. Following that, we may have our distributed parameters, our spatially variable parameters, pilot point multipliers for KH and SY. Once again, in the parameter data section of the pest control file, their initial values will be provided together with their upper and lower bounds. Control variables, which tell PEST how to calculate finite difference derivatives for those variables, will appear in the parameter group section of the pest control file. The second part of the pest control file, well, it'll have an observation data section, same as any pest control file. It'll have a command line section, and in that section will be the command which PEST uses to tell the operating system to run the model. More often than not, the model will be a batch file or a script file, which will cite a simulator, maybe with a pre-processor in front of it and one or a number of post-processors behind it. In other videos we talk about this as the model sandwich. So that's the pest control file. The parameter uncertainty file, most people who use IES or PEST will be familiar with this. This is where we characterize the prior probability distribution of model parameters. A parameter uncertainty file, and this is all explained in another video of this series, a parameter uncertainty file can have a number of sections. We may decide to characterize global parameters, the uncertainty of global parameters, using their standard deviations. Don't forget that if a parameter is log transformed, any uncertainty that we ascribe to that parameter in the parameter uncertainty file pertains to the log of the parameter. So here we're assigning standard deviations to our global parameters. And then, more often than not, spatially distributed parameters will have covariance matrices assigned to them. So that will be done through covariance matrix blocks. So this then is our parameter uncertainty file, exactly the same as the file that we'd use if we were using IES for history matching. And now for that extra file. This is called an ENSI specification file. This is where we assign parameters to different realization groups. So the ENSI specification file has different sections, and each of those sections has a header: realization group 1, realization group 2, and in this case non-realization parameters. For this illustrative model, we're assigning all parameters that belong to parameter group KH to realization group 1. Now we can assign parameters from other groups to the same realization group. Everything is flexible. But in this case we're saying all parameters which belong to parameter group KH, that is all KH multiplier pilot point parameters, will be assigned to realization group 1, and there'll be 120 realizations ascribed to that group. It's a good rule of thumb that the more information that the calibration data set carries for a parameter type, then the more realizations should be ascribed to that realization group in order to receive that information. So if KH is particularly well informed, you think, by the calibration data set, give it more realizations. In this particular case, we're defining a second realization group, and members of the parameter group SY, this is SY multiplier pilot point parameters, will be assigned to realization group 2. And we'll say there'll be 100 realizations that comprise this group. So that takes care of the spatially distributed parameters. Meanwhile, the global parameters or non-realization parameters will be listed in this non-realization parameter section of the ENSI spec file. Here we list the names of the parameters that will not be assigned to any parameter group. They'll be estimated individually. And if present, this section must be the last section of the ENSI specification file. Okay, now we're all set up. Now we're going to use the utility programs that I just showed you a little while ago to actually build all the files needed for ENSI inversion. Now in the description that follows, I'm going to go into some detail about what those programs do. But don't be deterred. Everything is automated. I'm going to describe what happens, but you don't have to know too much about what happens behind the scenes. Implementing ENSI based inversion is easy. I'm just explaining the details so you know what's going on. In practice, you don't have to know all those details. Okay, so let's now automate the setting up of ENSI inversion. And we do that, we start that process off, and we complete that process by running a little program called ENSI prep. To run ENSI prep, we type its name at the screen prompt. The first thing that ENSI prep does is it reminds us that there's two ways that we can designate observation groups as regularization groups. It's about to write a pest control file. We get to choose what option it uses, the old way of doing this or the new way of doing this. It doesn't really matter which you choose. But notice, ENSI prep is going to write a pest control file which is going to conduct regularized inversion, that is calibration. Next, ENSI Prep asks for the name of the pest control file that we wish to provide to it. I'm going to call it case.pst. Then for the name of the ENSI specification file, I'm going to call that ensispec.dat. Then it asks for the name of the parameter uncertainty file, param.unc. Shortly, ENSI Prep is going to write a whole lot of files, and it's now asking us for the file name base of all those files. We'll say case ENSI, case_ENSI. As I said a moment ago, it's going to write a pest control file in which pest is instructed to run in regularization mode. It needs a target measurement objective function. I'm going to just hit enter here. Often when I'm doing calibration, I get as good a fit as I can the first time I use pest, just to see how good a fit I can get. Then on subsequent pest runs, I'll set the target higher than that fit to prevent overfitting. But on this occasion, I want to see how well I can fit the calibration data set. So I'll just say enter. Finally, ENSI Prep asks for a random number seed. It needs this because it's going to generate random realizations of parameters. It's going to generate realizations of parameters that comprise these realization groups that we looked at a moment ago. So if it's going to generate random numbers, it needs a random number seed. Once we give it that seed, it does a whole lot of things and writes a whole lot of files. And we'll look at a couple of those files. One file we won't look at because it's a binary file, but it's worth noting that ENSI Prep has written it, is this file called caseensi.rls. This contains all the realizations that ENSI Prep has just generated. That's why it needed that random number seed, so it could generate realizations of the prior probability distributions of parameters that were assigned to realization groups. Let's look at the pest control file that ENSI Prep has just written. This is called ensiprep.pst because, it's called case_ensi.pst because we asked for case_ensi as the file name base of files that ENSI Prep would write. So here's the first part of that file. Pest is told to run in regularization mode. Here, ENSI Prep has told Pest use Broyden-Jacobian updating. The Jack update variable is set to 999. It's presumed we're using pest HP to do the inversion, and so this up test min variable, minimum number of lambda testing, minimum number of model runs to undertake in lambda testing is set to 20. This gives us as much alacrity as we can get in implementing Broyden-Jacobian updating to get as much as we possibly can out of any Jacobian matrix that we calculate. As I said before, this helps us in nonlinear circumstances. Here in the parameter data section of our pest control file are our global parameters, our non-realization parameters. This is just transferred from the original pest control file that we gave to ENSI Prep. In the parameter group section of the pest control file are the control variables that tell us or tell Pest how to calculate finite difference derivatives for these parameters. This too is transferred from the original pest control file. But then, instead of pilot point parameters, we have realization factor parameters. And see how they're named according to their function. Realization group 1, fac1. Realization group 2, fac1, fac2, fac3, etc. So realization factors replace the original spatially distributed parameters. Here in the parameter data section we have the initial values for those parameters and their upper and lower bounds. The initial values are 0. Here in the parameter group section we have how to calculate finite difference derivatives with respect to these parameters. So here we have realization factors for realization group 1, realization group 2. And there are as many realization factors in each of these groups as the number of realizations that we previously asked for to be assigned to each group. So here in the parameter group section, note these variables here. These are described in the PEST manual. If we're worried that perhaps model outputs have a little bit of granularity because of model numerical imperfections, PEST can take special precautions in calculating finite difference derivatives with model outputs with respect to model parameters. We invoke that when we assign these control variables for derivatives calculation. So we're making this whole process as robust as we possibly can so that we're giving PEST every chance to fit the data well. No matter how ill-behaved is the model, no matter how non-linear is the relationship between model outputs and model parameters. Here in the second part of the ENSI prep generated pest control file, the observation data section is just transferred from the original pest control file. We have one template file and one model input file now. This transfers realization factors and global non-realization parameters to the model, which we'll look at in a minute. These are all transferred through this template file to this model input file. And then we have a prior information section. We're doing ticking off regularization, and regularization constraints are expressed through these prior information equations. We're saying that each parameter should deviate to the smallest extent required to fit the data from its preferred value, and in each case that preferred value is its initial value. For global non-realization parameters, the initial values, the preferred values, were inherited from the original pest control file. For realization factor parameters, the initial values, the preferred values are 0. Now each of these prior information equations has a weight, and the weight is the inverse of the prior uncertainty of the respected parameter. For global parameters, the prior uncertainty came from the prior uncertainty file that we gave to ENSI prep when it generated the pest input dataset. The uncertainty associated with realization factor parameters we'll talk about in a moment. As we asked, the target measurement objective function is set very low, but ENSI prep requests that FIMFRAC, this is a regularization control variable, is set to 0.1. What this means is that whatever the current value of the measurement objective function, behind the scenes the target measurement objective function is always 1/10 of that. So regularization is always operating behind the scenes when we're using PEST to work in this limited dimensional subspace to calibrate the model. And finally, the command to run the model. We've got a new model batch file, and it's called ensibbatch.bat. Let's have a look at that. The second part of ensibbatch.bat is our original model batch file, model.bat. But up here in the first part of this batch file is the name of an executable program called ENSI mod. This is one of those 3 programs we saw before that the PEST-HP suite provides us to do ENSI-based inversion. The task of ENSI mod is to read realizations from the realization file, to apply the factors that are being estimated, and to calculate parameters that the real model can use. So this undertakes the transform from the limited dimensional parameter space in which we're working to the space of real model parameters. This applies the realization factors, combines the realizations to give us parameters that the model can use. ENSI mod also transfers global parameters directly to the model. It writes model input files using the same templates that we provided in the original PEST input dataset that we informed ENSI prep was case.pest and the template files cited therein. It uses those template files to write model input files. And so once we've run ENSI prep, we have everything we need to run PEST-HP. But before we do that, I just want to show you one more file. And the reason that this file is written will be apparent later. ENSI prep generates a parameter uncertainty file for our ENSI parameters. This file is named case underscore ENSI underscore prior underscore ENSI underscore param.unc. This file is a parameter uncertainty file, and it contains the prior uncertainties of all ENSI parameters. We'll see why we need this soon. The prior uncertainties of global non-realization parameters are taken straight from the parameter uncertainty file that we provided to ENSI prep. The prior uncertainties of these realization factor files, realization group factor files, are calculated as 1 over the square root of n minus 1, where n is the number of realizations in a realization group. The reason for this is described in PEST-HP documentation. So now we've got a parameter uncertainty file which provides the uncertainties of global non-realization parameters and of all the realization factor parameters. Now, remember I said before that when ENSI prep wrote the pest control file that we're going to use for ENSI inversion, it assigned a weight to each prior information equation. The weight for those prior information equations which enforce regularization constraints are the inverse of these uncertainties. So now we're ready. We have everything we need to use ENSI to calibrate our model. And to do that, we'll use PEST-HP. Now, to run PEST-HP, the manager and its agents must run in different windows. As is extensively documented in PEST-HP documentation, to run the PEST-HP manager, we type PEST-HP, the name of the pest control file, and then the TCP/IP port which the manager must open. The agents can be on the same machine as the manager or on different machines. Agent HP, name of the pest control file, the computer on which the manager is running, and the port that it has opened. If the agent is running on the same machine as the manager, we can use this computer name environment variable to provide the agent with the location of the manager. Or we can use the IP address. We can do that on the same machine or a different machine if we're running the agent on a different machine from the manager. Or we can use the manager's host name. In any case, we use as many agents as we can to get this whole process over quickly, and hopefully by running pest HP we will have calibrated our model using ENSI inversion, ensemble space inversion. And once we've done that, we're left with some small ENSI post-processing tasks to do to finish off this whole process. Now, Pest HP writes a lot of files. For example, the run record file tells us the history of the inversion process, tells us how good a fit we got with the calibration data set. Similar information is available in the residuals file. The file that we're interested in at the moment is the parameter value file. Pest or Pest HP at any stage of the inversion process have written up for us a parameter value file, and always this holds the best parameters that have been achieved up to that stage of the inversion process. At the end of the inversion process, the parameter value file holds optimized parameters. So let's have a look at that. It's named after the pest control file, in this case case_ensi.par, named after case_ensi.pst. Here are the optimized values for global parameters, non-realization parameters. Here are the optimized values for realization factor parameters. Unfortunately, that's not of much use to us. What we really want is the optimized values for native model parameters. So we have to now write a parameter value file which contains optimized values for model parameters. To do that, we use ENSI-mod. Now remember, we've seen ENSI-mod before. In the new model the batch file that runs the model that was prepared by ENSI prep, ENSI-mod runs ahead of the model. It does the transform from the limited dimensional parameter space in which we're working to full parameter space, to the parameter space that the model knows about. This applies the realization factors to calculate native model parameters from realizations and factors. Actually, ENSI-mod does a lot of things. To see what it does, you can just type its name at the screen prompt, and that's a short summary of the things it does. What we'll do is run it using this command. ENSI-mod case_ensi, the file name base that characterizes this ENSI-based inversion process, /p case_ensi.par. So we're giving ENSI-mod the name of the parameter value file that was produced during ENSI inversion. ENSI-mod knows what to do with that file. It calculates another parameter value file called case.bpa. Now this parameter value file is named after the original pest control file that we provided to ENSI prep. It's got an extension of BPA for best parameters. And here it is, case.bpa, optimized values of global parameters, and here are the optimized value of native model parameters, pilot point parameters for KH, for SY. This is what we need. So now we're going to use this. We're going to use this to populate a new pest control file. So there's the global parameters, the spatially distributed parameters. This is what the model understands. To build a new pest control file in which initial values are optimized parameters, we're going to use the parep utility. Parep stands for parameter replacement. This program comes with the pest suite. To see what parep does, you type its name at the screen prompt. That's a summary of what it does. We'll run it using this command. So parep, we give it the name of the parameter value file, and we say create a new pest control file called case_solution.pest, which is a copy of case.pest except initial parameter values, they shall be optimized parameter values. And oh, by the way, set the nopt max control variable to 0. That way, if we run pest, all pest will do will run the model once, calculate the objective function and stop. It'll also fill model input files with optimized hydraulic property values. So, parep, using this command, and there now is a new pest control file in which initial values are optimized parameter values. We can now run pest using that pest control file, and it will run the model, calculate the objective function, the contribution to the objective function by all observation groups, and then cease execution. So, that is basic ENSI post-processing. Now, before we finish this video, however, I'm going to say a few words about some of the options that are available to us for basic and more complex uncertainty analysis. I'll go through this fairly quickly. Details are in PEST HP documentation. The first thing that we're going to do is obtain a rough estimate of the posterior uncertainties of all our native model parameters. Now, before we do any uncertainty analysis, we have to get rid of regularization, and we're going to do basic linear uncertainty analysis to obtain, as I said before, a rough estimate of the posterior uncertainties of our native model parameters. To get rid of regularization from our ENSI pest control file, we use the subreg1 utility supplied with pest. So we say subreg1 case ensi.pest, we give the name of a new pest control file. I'm using NR for non-regularization. So now we have a new pest control file with regularization removed. I need, if I'm going to do linear analysis, a Jacobian matrix file which complements that file. Now remember, right at the beginning of this video we said one of the nice things about calibration is we get a Jacobian matrix. We're going to use that Jacobian matrix now. Whenever PEST does inversion, it records that Jacobian matrix at the end of every iteration of the inversion process. However, that Jacobian matrix corresponds to case ensi.pest instead of case ensi_nr.pest. So let's use the JCO to JCO utility to convert that matrix, to rewrite that Jacobian matrix so that it corresponds now to case _ensi_nr.pest. There we have it. So now we have pest control file case _ensi_nr.pst. We have a complementary Jacobian matrix file case _ensi_nr.jco. And remember, we've got the prior uncertainties of ENSI parameters written for us by ENSI prep stored in this file. So we have everything we need to compute a posterior covariance matrix for our ENSI parameters. To do this, we use the predunct7 utility supplied with pest. It asks for the name of the pest control file and it checks that there's a complementary JCO file. Now, posterior uncertainties, the two things contribute to the posterior uncertainties of parameters: non-uniqueness and the noise associated with members of the calibration data set, or whatever is responsible for model to measurement misfit. Predunct7 asks for this thing called the observation reference variance. This allows it to back calculate roughly measurement noise. The observation reference variance is the minimized objective function divided by the number of non-zero weighted observations. Let's pretend it's 2.32 in this case. Predicate 7 next asks for the name of the parameter uncertainty file, the prior parameter uncertainty file of ENSI parameters. We give it that name. Now it asks for the names of the files that it must write. It's going to calculate and record a posterior covariance matrix file for ENSI parameters. We'll ask it to store it in this file. It's also going to write an uncertainty file which cites this covariance matrix file. We'll give it that name. There's two options for calculating the posterior covariance matrix file. Normally the first option is fine, and it does the job. The file we're interested in is this one. We won't look at it, it's too large and it's pretty uninteresting. But we'll now run one more program that operates on this file, and that program is called post-ENSI-UNC. Post-ENSI-UNC will read that posterior covariance matrix of ENSI parameters, and it will calculate posterior uncertainties of native model parameters. So we run post-ENSI-UNC by typing its name at the screen prompt. We provide it with the file name base of the files which characterize this ENSI inversion process. We provide it with the name of the file that holds the posterior ENSI parameter matrix. And then we provide it with the name of the file that it must write. It then writes that file. Let's have a look at it. This is just a table contained within a file. The first column of the table contains the name of parameters, model parameters, not ENSI parameters anymore. Here are the global parameters, here are the pilot point parameters, the spatially distributed parameters. Here in this final column is an estimate of the posterior standard deviation of uncertainty of each one of those parameters. Now, this is approximate. It's approximate because it's linear, but it's not too bad normally. It's not too bad, especially for the global parameters. However, when it comes to these spatially distributed parameters, we really are asking a lot out of this process. We've taken a posterior covariance matrix that's applicable to a subset of parameter space, and we've tried to calculate uncertainties for all parameters that occupy the entirety of parameter space. Now, this is going to be inexact, but it's something, and we can use these posterior uncertainties, parameter uncertainties that we calculate to get some indication of how much history matching has been able to reduce the uncertainties of native model parameters from their prior uncertainties to their posterior uncertainties. It's approximate only, but it's easy to calculate and it is indicative. So now we'll finish this video by briefly exploring options of how we can do more comprehensive predictive uncertainty analysis once we've calibrated our model using ENSI. The first option is probably the most comprehensive, but also the most numerically intense. So, what has ENSI given us? ENSI calibration has given us good fits between model outputs and the calibration dataset, hopefully. It's also given us a set of native model parameters that are near the centers of their posterior probability distributions. So now we use PEST-PP-IES, but we've given PEST-PP-IES a head start. We give PEST-PP-IES a covariance matrix that encapsulates the prior probability distribution of native model parameters. but we tell it that when it's generating random samples from the prior parameter probability distribution, to center those samples on the parameters that ENSI gave us. So by doing that, we're starting off with an unbiased set of parameters, hopefully, that allow IES to fairly quickly adjust the other set of parameters until they give us as good a fit with the calibration data set as ENSI gave us, provided of course that we tell PES-PP IES to use enough realizations. So hopefully within a few iterations, PES-PP IES adjusts those samples of the prior centered on ENSI calibrated parameter set until all of those samples fit the calibration data set well, hopefully as well as ENSI fit the calibration data set. It places all those samples of the posterior native model parameters into a CSV file. Once we have that CSV file, we can run the model into the future to sample the posterior probability distribution of any prediction that we're interested in. So that's option 1. With option 2, we stay in ENSI parameter subspace. So once again, what has ENSI given us? It's given us good fits between model outputs and the calibration data set. It's given us ENSI parameter values that are near the centers of their posterior probability distributions. Once again, we use PES-PP IES, but we stay in ENSI parameter space, that small dimensional subspace in which ENSI has been working up until now. We tell PES-PP IES that the prior probability distribution of ENSI model parameters is in fact the linearized approximation to the posterior probability distribution of ENSI parameters that Predunc 7 gave us a while ago. So now we are really giving it a head start. We're centering random parameter field generation on the calibrated ENSI parameter set, and we're telling IES that the prior is in fact a linearized approximation to the posterior. If we have enough PES-PP IES realizations, very quickly PES-PP IES should give us a CSV file containing random samples of the posterior ENSI parameter probability distribution, with all of these samples fitting the calibration data set just as well as ENSI was able to fit the calibration data set. Our problem now is to take the contents of this CSV file containing ENSI parameter samples and create a CSV file containing native model parameter samples. This can be done using the ENSI mod program that we've already seen. It will then give us a CSV file containing samples of the posterior native parameter probability distribution. Once we've got that, we can run the model into the future to sample the posterior probability distribution of any prediction that we care about. Option 3 is a little bit similar in that we stay in ENSI parameter subspace, but this time we just do linear analysis. So what has ENSI given us? Once again, good fits between model outputs and the calibration data set. And it's given us ENSI parameters that are near the centers of their posterior probability distributions. During the ENSI calibration process, we obtained a Jacobian matrix. Remember, I said way back at the beginning of this video that one of the nice things about calibration is the fact that it gives us a Jacobian matrix. We can now calculate a predictive Jacobian matrix, and this doesn't take too long to calculate. We just run the model into the future as many times as one time for each ENSI parameter, and because we're working in a small subspace, a parameter space, that's not too many model runs. So now we have a calibration Jacobian matrix we have a predictive Jacobian matrix. Then we can simply do linear analysis using utilities available through the pest suite to look at predictive uncertainty and ancillary things like data worth, parameter type contributions to predictive uncertainty, and other nice things that linear analysis will give us. So that's option 3, and all the while we're staying in the original ENSI parameter subspace. This is probably the quickest option, but a little bit approximate. So that's pretty much it. That's ENSI calibration and some of the options for what we do after ENSI calibration. So before finishing up this video, we'll just briefly summarize some of the contents. ENSI is very robust. It's easy to implement. It's numerically cheap. It generally gives us good fits between model outputs and field observations, even in difficult non-linear circumstances. And it provides a sound basis for ensuring parameter and predictive uncertainty analysis. ENSI is implemented using programs available through the PEST HP suite. That brings this video to an end. Thanks for watching. See you next time.